Thank you very much for this invitation to talk about the challenges of big data for the social sciences. I'll try to do justice to being sort of the kickoff speech here this morning. Let me ask you a question first. How many of you are social scientists versus policy? Okay. Well, a lot of what I say applies to social science and policy. So here's what I'm going to do. To keep things moving along, I'm actually going to organize my main arguments into 12 points. So I switched the title a little bit because there was one or two more that I wanted to squeeze in. And I'm going to talk about this as if it were a 12-point program. Now, I'm not going to be semi-humorous because I'm not making the point that we have to overcome some deep problem or damaging problem through conscious change, but I am making the point slightly. So to get things started, I'm going to start and just move on with the points. Our first challenge. The first challenge is understanding what we mean when we talk about big data. What do we mean by big data? Well, the simple answer to the question of what big data is has to do with size. That's a simple answer. It's quite simply data on a scale that is so large that we can't manage, analyze, or make sense of it using techniques that we've applied to smaller and more traditional types of data in the past. There is a more complex answer, and this has to do with changes in the nature of the data that we use that enable the massively big scales of the data size, especially the way that the data is produced, formatted, and communicated. It's not only the size of the big data, in other words, that causes us to need to rethink how we use it for generating knowledge, but it's also the manner in which this data is generated. It's also the tools that shape how we analyze this data and how this structures the knowledge that we generate from analyzing this data. Let's take an example from social media, including what you might have seen for promoting this talk, for example, on the micro-blogging social media service Twitter. Twitter data has been shown to contain very rich information if filtered properly. I'm currently, for example, involved in an EU-funded project to analyze political knowledge and political engagement in the European Union by looking at Twitter data in more than 12 countries surrounding the 2014 European Parliament elections, looking at the communications between political elites and mass publics. A tweet is limited to 140 characters of text, but each of these tweets with their 140 characters of text comes with a vast quantity of additional data known as metadata. You've probably heard this term, even if you're not completely sure what it is. A single tweet, in fact, contains about 2.5 kilobytes of metadata in the format that is available from the Twitter application programmer interface, or the API. And here's an example of some Twitter metadata in the format that you can obtain it from the publicly available API of Twitter. Now, by modern standards, 2.5 kilobytes is not very much, but it might seem more impressive if we consider that the Apollo guidance computer, which was used to carry astronauts across 356,000 kilometers of space from the Earth to the Moon and back safely, contained only about 16 kilobytes, which is enough to store about 6 of these tweets and their metadata. Now, fortunately, computing power has made some pretty impressive advances since that day, and to handle the current daily volume of about 500 million tweets per day from about 288 million users, we have slightly more powerful hardware. Other examples of the size of big data are even more mind-boggling. So just to give you a few examples. There are currently about 3 billion Google searches every day. On U.S. equity markets, about 7 billion shares are traded every day, about 2/3 of these by computer algorithms. To the video sharing service YouTube, about 1 hour of video is uploaded every second, which is a lot of surfing squirrels and dancing cats. The online retailer Amazon.com has been known to sell over 400 items per second on its busiest days. And on Cyber Monday alone in 2013, from what I could find on the internet, there are 36.3 million items sold, for example. 36.8. On the social media site Facebook, there are more than 30 billion pieces of content. There are web links, news stories, posts, etc., that are shared each month. So when we talk about the big in big data, we mean the sort of big that involves millions, billions, or even more. It requires us to speak in a new language of gigabytes, terabytes, and petabytes. These are data volumes that are on a truly staggering scale. We could say cosmological scale, scales that defy comprehension. So that's my second challenge, understanding what makes big data different besides simply size. So let's make a distinction here because I'm talking about social sciences. I'm really only talking about social big data today. And in this way, I want to distinguish social from big data about the physical world, even though this is an oversimplified dichotomy. And by social, I mean a broad category, including the economic, the political, the social, the legal, the financial, the business, psychological activities. In other words, human-created activities. What makes big social data different is that it comes not just from human activities, but very often from the recorded byproduct of these human activities. Sometimes, as in the case of Twitter, they are generated by new activities that are linked to the data produced, because tweeting is not an innate human activity. It's something that was created by the availability of this service. But a lot of big data does come from these new activities. Big data also comes from improved measurement of existing activities. This is the process that Ken Sukier and Victor Meyer-Schoenberger termed datafication in their excellent book, Big Data, a revolution that will transform how we live, work, and think. Datafication refers to the process of recording information in a systematic and quantified format that we can tabulate, cross-link, and analyze. Social datafication reaches extensively into our modern lives in ways that many of us may not even be aware. Whether you like it or not, whether we like it or not, we are all generating big social data every day. Many of you probably at this very instant. That's right, sitting here listening to this talk, you're generating big data. Now, how are you doing that, you ask? Well, reach in your pocket, pull out one of these. You probably have some sort of phone, smartphone. If you do, then it's probably sending your location at regular intervals to Apple, to Google, or to your mobile service provider. That's true even if you have a dumb phone for the last one, by the way. It's sending your search terms. If you're Googling, who is this Ken Benoit guy? Let's look at his webpage at LSE. Your search terms are being recorded by Google or whatever search you're searching for. If you go to the Guardian's webpage and you search for news, all your search terms are recorded, probably used by some academic in a study 2 months later. You're letting Google and Apple have access to your email content. You're purchasing goods, perhaps, or using direct payment methods through your phone. And of course, you're sending text and internet messages. You might be accessing social media. Maybe you're tweeting right now that I just said you were generating big data and therefore fulfilling that prophecy. Of course, there is this thing that phones used to be used for, which was making phone calls. The metadata for these calls is legal for governments to analyze in the UK and in the USA, for example. What about your wallet, right? What about this thing here? So you might say, well, I don't have any technology, but I've got one of these. Well, your credit cards record your purchases. Your loyalty cards transmit even more information about your purchases. Your Oyster card tells Transport for London where and when you traveled. Do you have a fitness bracelet? Maybe one of these Apple Watches or Fitbit or Jawbone or something like that. Well, they actually record huge databases of the steps you take, your sleep patterns, the calories you eat, the calories you burn, your weight, even your body fat percentage if you have a smart scale. Does this sound pretty scary? Well, in a previous era, it was difficult, it was costly, and it was ethically problematic to recruit people to wear devices that would record even a fraction of this information. In the current era, people queue up for days outside of Apple stores to buy these things at great cost so that they can generate this data for commercial interests. This information is wearable. It's something that gets transmitted all of the time, and legally speaking, technically, and I'll talk about this later, with the user's consent. Now, whether that's informed consent or not is another issue, but we'll talk about that shortly. So big data is different because of its size, because of the way that it's produced, and together these things make for some formidable technical challenge, which brings me to challenge number 3, harnessing the computing power to match the size of this big data and its complexity. Big data is very different from the classic sort of data sets, the small data sets that we're used to working with as social scientists. In most social science research, we need new tools to unlock the secrets of big data. We also need more powerful computing hardware, more powerful than what we're accustomed to using. Big data is not your average consumer household survey. It's not the British election study. It's not a data set about firm spending. It's not a collection of legal decisions or published results of election data that you might get from a website. It's not the sort of data you can email to a colleague. It's not the sort of data you're going to go to a website and download into an Excel file. This is data on an unprecedented and sometimes mind-boggling massive scale. Now, the good news is that computers are getting more powerful every year. Let's consider one of the previous generation's most complex problems, the Human Genome Project. This was a project founded in 1990 with $3 billion in funding from the U.S. Department of Energy and the National Institutes of Health. It was expected to take about 15 years to sequence the entire human genome. It actually only took about 10 because of advances in computing power. Well, today, with the computers available, you can actually do it in less than 3 days to sequence the entire 3+ billion base pairs in the human genome. Here's an even more. So here's, this is old school now. So if you want a really advanced project, the Square Kilometre Array is an international consortium of astronomers that are constructing this massive telescope array called the Square Kilometre Array, because that's actually the size of the, if you were to put together all the radio dishes, satellite dishes, it would cover 1 million square meters. And this is the biggest and most accurate radio telescope ever constructed. It's estimated that this will generate an exabyte of information per day. What is an exabyte? An exabyte is 1 × 10 to the 18th, or 1 with lots of zeros after it. This is more than twice the amount of information that is communicated daily on the entire internet. So 1 exabyte could hold 100,000 times the printed material, or 500 to 3,000 times all of the content of the Library of Congress. The most powerful computers that exist today can currently not handle this volume of information, but companies and governments are working on it. So ambition here is fostering innovation. Now, earlier I mentioned the social platform, media platform Twitter. A standard desktop with a generous 16 gigabytes of RAM or memory would be able to fit about 6 million tweets into active memory. If you have a standard 1 terabyte hard drive, which is more than 187 million times how much storage capacity the Apollo guidance computer had, then you could store about 400 million tweets in their raw form, assuming that nothing else was on the hard drive. That's only 1 single day's worth of Twitter. So big data are big scale, and for us to analyze this, we have to use tools that we normally do not use. We have to use large-scale computing resources. We have to build efficient databases. We have to figure out how to use parallel computing, perhaps cloud computing. We're not used to doing any of these things in social science. Now let's take things to a slightly more theoretical level. So challenge number 4 is that we should be using big data for social scientific explanation rather than just prediction or pattern recognition. In other words, explaining things rather than predicting things. Big data has led to the growth of a field called data science. Data science is generally defined as the extraction of knowledge from data, but it's specifically associated with the goals of prediction or pattern recognition, especially for big data. This field used to be called data mining. That was an approach that didn't get much respect in the social sciences. But now that it's been rebranded as data science, using new tools and concepts from computer science, then data science has become a formidable rallying cry and a focal point for education, employment, and funding. I'm guilty of this too. I'm teaching a summer school course about data science, and we're currently full. So people want to learn and do data science. Data science and its association with big data is associated with extracting knowledge from this sorts of data. But my point is that we have to reconcile this type of knowledge with the sort of knowledge that we have been concerned with for the standard canon in social science. Let me cite a much oversighted essay, so I'll go fueling the fire. This was by Wired magazine editor Chris Anderson, who declared in an article, "The End of Theory." He was in essence saying that while our traditional objective used to be to understand causes, that we can now be content to identify correlations. We have a quantity large enough to provide comprehensive associations of patterns without this unnecessary focus on causation and explanation. He said, and I quote, "Who knows why people do what they do? The point is they do it, and we can track and measure it with unprecedented fidelity. With enough data, the numbers speak for themselves." Anderson's paragon was Google, and how Google turned machine translation of natural languages on its head by using statistical models for translation rather than the rule-based models that linguists had constructed previously. This was an extension to Google's approach to ranking web pages and search engines based on the web of linkages to pages of similar content, not based on any prior human assessment or any expert assessment of what was relevant. This approach to focusing on predictive accuracy, however, instead of understanding causes, carries very serious risks for social science. Social science seeks to make stable generalizations, not to focus predictive power on any particular, quote, training set. The lens of social science points to different questions than the typical application of data science to generate knowledge from big data. A typical data science problem, for instance, could be to predict what movie you would like to watch or what song you would like to listen to based on your previous preferences and based on the association of preferences of people who also liked a particular song that you indicated that you liked. This is what Netflix uses, for example, to issue recommendations for this purpose. Now, Netflix is not concerned with analyzing underlying psychological theories of consumer preferences or any other preferences. They're only concerned with maximizing predictive accuracy out of sample. Rather than having causal variables and control variables, they simply consider all data to contain features, and these features are transformed, added, or dropped according to the criterion of whether they improve prediction. Our concern in social sciences is very different from this sort of focus. Rather than chasing prediction, social science is more fundamentally concerned with identifying causes, which brings me to challenge number 5. Integrating data science with social scientific developments in causal inference. When I say causal inference, I'll explain what that means. But social science has come a very long way towards setting conditions that identify causes of events as opposed to correlations, yet these developments from social sciences haven't filtered in yet to the analysis of big data. Let me show you a paper by Valenzuela, Halpern, and Katz, who studied the correlation between social networking usage and happiness in marriage and relationships. Using both aggregate data consisting of divorce rates and social networking usage and some individual level data from surveys, they found a positively and statistically significant relationship between Facebook usage or Facebook penetration and divorce rates. In their estimates, a 20% increase in the share of Facebook users in a given United States state was associated with a 4% increase in divorce rate the following year. Now, to be fair, the authors did acknowledge the possibility that recently divorced people and those in troubled relationships may turn to Facebook as a remedy or to find new partners. However, that did not prevent the research leading to conclusions, of course, that social networking usage reduces marriage and well-being. They said the following, things like excessive use of social media can create difficulties in one life, it can trigger unhappiness and ultimately divorce. Facebook creates an environment where you make your partner jealous, you can harm your relationship, and of course it enables you to find extramarital affair partners and therefore contributes to cheating. Now the problem here is that focusing on these rates to predict divorce is doing nothing but speculating on the causes, because these quotes, which I've taken here, not too entirely out of context, are just speculation as to the causes. That's all that they can do in the absence of some strategy for causal identification. Because of the data science's association of scientific rigor, however, with the methods used in this study, popular media is happy to jump on a result like this. In fact, these results have even been cited as evidence in court cases about divorce. It turns out that overemphasizing prediction or focusing on causation rather than, or correlation rather than causation, causes the validity of our explanations to break down very quickly and to lead to absurd conclusions if they're applied naively. In the social sciences, by contrast, we have long moved past casual approaches to causal effects. In social science, we have a completely different goal from prediction. Rather, our goal is to estimate isolated marginal effects which can be identified as causal. We do this through the careful choice of variables, not machine selection of predictors. I'll give you a quick example from my own field, which is political science. This is the question as to whether appearing earlier on a ballot, as higher up on the ballot, helps candidates to receive more votes, something that might be of interest to anyone trying to receive more votes. The objective in this study is to optimize, to figure out optimal institutional design. In other words, how do you create a ballot that is the most democratically fair? You know, someone does have to go first on the ballot. So the question is, does appearing on a ballot earlier improve your votes, all other things being held equal? This raises a very good question. How do we hold other things equal? Well, the answer in this case is actually fairly easy because ballot order is effectively randomized in many contexts. In some, alphabetical order is used. In others, strictly random order is used through drawing lots. So colleagues of mine, Daniel Ho and Kosuke and I, published a study in 2008 that studied ballot order effects in California. California uses a randomized alphabet that is equivalent to having a random treatment of the effect of ballot order. With random treatment, there are no confounding variables. In other words, variables that could result in a bias in the absence of if they were correlated with the treatment. This means that few to any additional variables need to be included in such a model, but also that predictive accuracy, if we were to judge this by data science standards, predictive accuracy is low or even non-existent. The idea here is to use a treatment such as this to estimate causal effects by comparing the differences between treated cases and those with potential outcomes that might have been untreated by assuming that the units have some stable treatment effect and that they can be considered equivalent with all respects except for that of the treatment. This is a plausible assumption when the treatment effect is randomized. And in their study, what they found was that there is a measurable boost to being first on the ballot, and that this effect was stronger for minor parties rather than major parties, and more so in primaries than in final outcomes. Now, if you were to judge this by data science standards, say minimizing root mean squared error, which is a fancy way of saying predictive accuracy, the results would be terrible. But that was not the objective of this study. The objective was to estimate the causal effect of ballot ordering on outcomes. This is an excellent model of that. It is a terrible predictive model of who actually wins the election. That is not of any concern to social scientists because our goal is to focus on the differential effect of a treatment, not the predictive accuracy of a model. The confusion as to which objective was part of the objective of the study was what caused these confusing and misleading outcomes for the Facebook study that I cited earlier, because it didn't distinguish correlation from causation. It provided no way to isolate the causes. And the particular problem here was that this observational study was characterized by extreme non-random assignment of treatment, in other words, the level of Facebook usage, among groups without respect to their values of marital unhappiness, which left the exact nature of the relationship between cause and effect undetermined. Challenge number 6. We have to recognize that human beings change, and therefore patterns constantly change. Now, this may seem obvious to us, and may not form the first concern of natural science data scientists, simply because astronomical units or molecular units do not change as a result of being observed. And I'll make some apologies if there are any quantum physicists in the audience. Social big data and the way that it's collected frequently does change as a result of being observed. Here's one of Google's many projects. We call this Google Flu Trends. This is a model of influenza which is based on search terms associated with the flu. Around 2009, Google began using its database of search results to come up with 45 search terms that had a strong correlation between predicting national flu outbreaks. This was based on processing 450 million different mathematical models, a massive application of computing power that is fairly typical in the field of data science. The following year, it helped to predict the H1N1 flu, or the avian flu, you might remember, faster than the actual reporting of cases from the Centers for Disease Control. However, around 2012, it began to fail quite badly. It began to overpredict the incidence of flu by more than double of the CDC estimates. Now, why did this happen? Well, writing in the journal Science about the parable of the Google flu story, David Lazar and colleagues from Harvard University warned that the quantity of data does not mean that one can ignore foundational issues of measurement, construct validity and reliability, and dependencies among the data. They also pointed to why the Google flu trend predictions had failed. First, the nature of the search tools that had been used for the basis of prediction had changed because Google modified them, especially in 2012, when it changed its search machinery more than 86 times in June and July alone. Furthermore, that data that was harnessed for predicting flu was not actually designed, it was never designed to detect flu. It was a byproduct of something that happened. It was from secondary data. And finally, the data that were used for this were not something that you could actually replicate scientifically or even test. In fact, the full 45 search terms that were the basis of this study were never made public. And that's something I'll come back to shortly. Challenge number 7. We should never make inferences from data, big or small, without understanding the data sampling process. Let me take this opportunity to debunk a pernicious notion that has gained surprising appeal among big data proponents, but I think is dangerously misleading. I call this the myth of n equals all. In classic sampling, we draw a randomly selected subset from a large population in order to make inferences about that population. The classic reason that's given for sampling is that we don't have the resources to get data about an entire population. So we make it effectively unobservable. But the n equals all argument suggests that in the era of big data, we do have the resources to observe the entire population, and therefore we no longer need to sample from it. Instead, we can use all available data without sampling and compute the population parameters directly without having to estimate them from a sample. The implication is that we don't need information, we don't subject our information to sampling error because you take the data directly from the population. Well, what is sampling error anyway? Well, in the best case, this involves random noise, but in the worst case, sampling error involves a form of bias. This is also the risk that comes from the n equals all misconception. If we want any example, we can turn to something that will be known to any student of polling, a famous example from the 1936 Literary Digest poll to predict the U.S. presidential outcome in that same year. This was conducted largely among the Literary Digest magazine's own readers, and it concluded that the Republican candidate, someone you probably never heard of, named Alf Landon, would win in a landslide. This was a poll that was started in 1890 by the Literary Digest, and it had correctly predicted all 5 previous election results using its polls. In 1936, it used a postal card poll, and it claimed to have asked an entire 1/4 of the nation's voters which candidate they intended to vote for. And they received 2 million return postcards on October 31st. No poll today ever takes a sample of 2 million people. And it issued its prediction that 57% of the vote would go to the Republican candidate Alfred Landon. However, Roosevelt ultimately won with 61% of the popular vote. The problem here was not that the Literary Digest readers and the car owners that were registered that it used were a biased sample, but also that it had a significant non-response bias. The resulting vote estimate was therefore off target because the selection mechanism, in this case being included in the polling, was correlated with the expression of vote intention. So would n equals all solve this? Would gathering even more voters have solved this? Well, if all refers to the sample of the readership and car membership, car ownership database, then the answer is no. Even if this sample had been representative, there would still be a problem of bias that comes from self-selection, which in this case meant agreeing to take part in the poll. And this is something when we do sort of big data polls, people who opt to use the devices and participate in the data gathering are very much self-selected. So when you gather data from your banking cards or your fitness watches or your Oyster cards or your mobile phones with GPS signals, even if we got n equals all social media users, we're still getting a sample. We're not getting everyone, and there's still great potential for bias in this population. We still need to be aware of sampling procedures. So the lesson here is that data comes from a sampling process no matter how much of it we collect. It doesn't matter how much data we have. The numbers, contrary to what Chris Anderson said, never speak for themselves. Challenge number 8. We have to integrate qualitative methodologies with quantitative and computational methods when applied to big data. So integrating qualitative methodologies. And I'll speak very briefly on this point, but I think it's an important point. When we generate social science knowledge, we've long recognized the need for methodological plurality. That different varieties of knowledge offer different paths and greater fruitful paths to greater understanding. No purely quantitative understanding of the social world exists, and therefore qualitative research may be the best or even the only way to gain leverage about many important problems. Data science and the study of big data, however, is currently focused overwhelmingly on quantitative and algorithmic methods rather than qualitative understanding. Yet if we want to understand many of the qualitative or the causal mechanisms and the context in which big data is produced, if we want to understand the understandings or get into the understandings of the participants, this would be greatly aided by using qualitative methods that we have long refined in the social sciences. The challenge for the social sciences is that data science has yet to come to any agreed terms of qualitative research, and qualitative researchers also find the technical barriers of working with big data to be fairly limiting. So integrating our social science toolkit from qualitative research with the technical challenges of big data and using this fusion to ask and answer better questions from big data is a key challenge. Challenge number 9. We must integrate ethical understanding of the issues involved surrounding big data with technical understanding. So this has to do with ethics. And here the point I want to make is even shorter, but it's nonetheless crucial. We need to bring the expertise and understanding in the legal and ethical fields up to some rough parity with our technical understanding of big data and big data issues. This has to do with maintaining ethical standards of research in the social sciences. A key part of any ethical research policy of the sort that would be needed to pass what we call an IRB or Institutional Review Board involves informed consent. The private companies, however, that record social data, big social data, are not bound by institutional review boards, especially when users have voluntarily agreed to very liberal data-related provisions in the providers of terms of service. For the free providers, quote, free, such as Google, Facebook, or Twitter, these terms of service can be very complicated. How many of you have read the detailed end-user license agreements that come with your Facebook or iPhone? Well, here's an example from Facebook and the Apple. You're essentially licensing it to use any content that you post. You're giving Apple a scary amount of rights, and I do this. You know, I freely give them my information. I'm not telling you shouldn't. It's for you to judge, but you should, you might want to be aware by reading this thing. It's only a couple hundred pages long and requires a legal degree. Yeah, 2 legal degrees. So these essentially grant the right to companies to use and reuse their data, your data, for their own purposes. And in the cases of devices or software with geolocation facilities, this can include sharing your movements. For some providers, they can use their reach and power to conduct experiments on their users and still have this lie within their legal terms of service. In a controversial article that was published last year in the Proceedings of the National Academy of Sciences, Kramer, Guillory, and Hancock reported the results of a Facebook experiment that involved manipulating the posts in their feeds. During a 1-week period in July 2012, Facebook intentionally manipulated the feeds of 689,000 English-speaking Facebook users in order to estimate whether showing more positive posts in a user's Facebook feed was an emotional contagion that would inspire users to post more positive things, him or herself. Not surprisingly, the research found that it did, but what sparked more discussion than the actual results were the ethical concerns surrounding the study. Facebook performed this experiment on its users unannounced, without any form of informed consent beyond the claim that this fell within the user's terms of service that they'd all agreed for when signing up for Facebook. Many of these EULAs push the bounds of legality and the bounds of ethical concerns. Recent controversies sparked by the revelation that some companies may have been sharing private data with U.S. government agencies have only added to this debate. Even without that, we could say that the ethical issues are more complex because they are more complex than the sum of the individual data sources. The reason for this is that the analysis of multiple big data sources by linking them together can provide a far more penetrating and potentially invasive portrayal than any single provider can, or governed by any single terms and conditions of usage. So legally these things may pass for consent, but ethically they may not pass for what we call informed consent. And our challenge in the social sciences is to find an appropriate balance of this, especially when this data is being provided for secondary social scientific purposes, purchased or obtained through commercial sources. Challenge number 10. We have to learn new skills and we have to adapt the way that we work. Now this challenge strikes us where we live. And by we, I mean social scientists, especially privileged senior academics who are supposedly the keeper to the keys to the gates of the academy and the expert knowledge that lies within it. The reason for this is that if we want to make sense of our changing world, then we have to change the way we practice social science. Whether we acknowledge it or not, the changing nature of the social world has devalued our most treasured asset, which is expertise. The tools that we learn in graduate school and possibly that we teach to students may be ill-suited to analyzing big data. This is true for both our methodological approaches and for the technology that we use. Part of this problem is that, and I say by we I mean, for example, tenured research professors, our skills may be at least a generation old. Re-education takes enormous energy. Just ask medical professionals. We all agree that it would be dangerous and irresponsible for doctors not to keep abreast of innovations in medical knowledge. So what makes social scientists any different? Now on the challenge of re-education, if you're a social scientist, I feel your pain. But gaining new skills is something that we have to do, and this includes teaching things to our students that are not currently traditionally taught in social science programs. In particular, I think that no social science researcher who works with data or analyzes data can be fully data literate unless they learn some computer programming, what people these days call coding. Now, let me repeat that. Data literacy means computer programming. This in turn implies some knowledge of algorithms. This in turn implies that we need to learn about data structures. Taken to the logical extremes, and all competitive and advanced areas of knowledge do take things to their logical extremes, this means integrating computer science into the social sciences. I contend that every modern institution of higher education that claims to be doing social science research needs some computer science representation, some department or field of computer science. That some exposure to this by all students should be as mandatory as learning basic math skills. This is hard, but let me be perfectly clear. Understanding the technical basis of big data means using big data. Understanding the technical basis of big data means that we are analyzing data as astronomers. If we don't understand the technicalities and we're simply talking about it, we're just doing astrology. Another way that we have to change means breaking down disciplinary boundaries. It's long been true that disciplines productively share, import, and export research and methods. Economists are probably the most voracious in this respect. But with big data, this is more true than ever before because big data doesn't care about disciplinary boundaries. Now, the nature of expertise, of course, is that it is narrow and we simply lack the intellectual capacity and the lifespan to become experts in all fields. So this points to one more area in which we should change our practices, involving collaboration not only within our disciplines but across disciplines. Collaboration with colleagues in areas where we are less expert offers a means to complement our expertise and to exploit real synergies and to break down disciplinary boundaries and contribute further to knowledge generation. Challenge number 11, we have to open up closed research. The complexity of big data underscores our need to work more openly. What do I mean by working openly? Here I mean just that. It means working openly and subjecting our most complex scientific tasks to scrutiny. We offer up our work to a vast, unidentified critical audience and give them the chance to prove us wrong. And the more complex the research, the more important this is. Why is this true? Because making mistakes when working with big data is not a risk. It's something that is certain to happen. This is true for systems of any complexity, but it increases with complexity. The more complex the system, the harder it is to find bugs, which is the software term for programming mistakes, and the unintended consequences that can arise from bugs. So I'm saying that there are huge advantages to doing open research, to making research methods, data collection, software, and analysis open, to make replication possible, replication being one of the foundations of science. The ability to replicate a study provides basic trust that the results were not fraudulent. This is an area where social sciences have made tremendous progress in the last decade, but in some it's not an even thing, but we are making things available. And here I'm showing you something from a website called GitHub. This is a colleague of mine at New York University. They've just published a paper which involves big data analysis. They have set up a GitHub page that allows anyone to access every step that they took from data collection to analysis to producing final tables and figures. You can clone this. You can even suggest changes if you find a mistake. It opens everything up to scrutiny. It allows people to extend the study, and it allows people to verify that the research was done in a correct fashion. To trust research, we must be able to reproduce it. There are no secret sauces in science, and there are no black boxes. As I stated when introducing this last challenge, this hits us where we live because our key assets as intellectual and university leaders is expertise. But if you view this more broadly, the process of questioning, challenging, and improving knowledge practiced by programmers on websites or social scientists that I've shown you using GitHub is no different from the model of cumulative knowledge generation that we are supposed to embrace as scientists and scholars. This is a true meritocracy where the currency is information. Good information is rewarded and recognized. Bad information disappears. This is the sort of open, collaborative, and intellectually competitive model that we need to apply to bring big data into the fold of the social sciences. Now, you might be expecting a 12th and final step, but I'll tell you here that, in fact, I lied. There is no 12th step. The lesson, then, is always be skeptical, especially of so-called experts. So, on that note, I'll turn things over to the chair and to you for any questions.
Thank you, Ken.